Hello, algebra students. We are going to be working today on a pretty tough lesson. Now, the main thing we're going to be doing in this lesson isn't that tough. The main thing we're going to be doing is called prime factorization. That sounds a little scary, but all we're going to be doing is finding the prime numbers that multiply together to make a larger number. So, for the number 100, there's a set of prime numbers that multiply together to make the number 100. For 51, there's a set of prime numbers that multiply together. We call that set of prime numbers the prime factorization. Every number has a prime factorization. Even prime numbers have a prime factorization. They are their own prime factorization. But like the number 1000, the number 5, the number 26, any number has a set of smaller prime numbers that you multiply together to get that larger number. Or in the case of the number 5, which is already prime, the prime factorization is just itself, because 5 times 1 is 5. Okay, so we're going to learn how to do prime factorization. We're going to be using this as a tool for doing something that's a little harder. And I'm doubting that you've ever done this before. That's one of the reasons this lesson is hard, because a big part of this is new. We're going to find the greatest common factor. That's what GCF stands for, the greatest common factor of expressions. Now, our expressions are always going to be either binomials, which have two terms, or in the case of this letter I, this last one, we're going to be working with a trinomial, 1, 2, 3 terms. But actually, what we're going to find is these are pretty simple problems because we're going to be working with binomials and trinomials that obviously have lots of things in common. I'm going to tell you, this is a tool, okay, that we're going to use in much more complicated stuff later this year. So if this seems complicated now, I need you to understand you're going to have some stick-with-itness here, because later on this year, we're going to be using this as a tool to do things that are harder. And if you can really grasp and retain the skills you learn in this lesson, it's going to make later lessons a whole lot easier. Okay, let's get started. The first thing we're going to do a prime factorization for the number 100. And this is how you do it. You figure out what numbers multiply together to make 100. And I did 2 times 50 because I always like to start with the smallest number possible. And for an even number, I can factor out a 2. We call this factoring out numbers, or factoring. So I'm factoring 100 into 2 times 50. These are the two factors that make up 100. You could have also done 10 times 10 if you wanted to, or 4 times 25. Here I'm going to do 2 times 50. And then 50 could break down further. 50 breaks down into 2 times 25. 25 breaks down into 5 times 5. And now, because all of my terminal numbers at the end here are prime numbers, I have my prime factorization. What I can say is if I multiply 2 times 2 times 5 times 5, all of my ending numbers, if I multiply those back together, I will get 100. And I observe that these are all prime numbers. So what I can say is the prime factorization of 100 is 2 times 2 times 5 times 5. There it is. Now, the correct way to write this, the technical correct way to write this is 2 squared times 5 squared. Instead of writing out 2 times 2 and 5 times 5, I will accept either way. But this is the better way to do it for some applications. Actually, a better way to do it today is just to write out 2 times 2 times 5 times 5, or just write the numbers next to each other. Okay, let's do an easier one, 51. If I look at 51, I realized by a divisibility test that 51 is divisible by 3 because 5 and 1 add to a number that's divisible by 3. These divisibility tests that you learn in the skills bank, super helpful when you're doing factorization. So if you're really good with those divisibility tests, it's going to help you out a lot in this lesson. 3 is prime, can't be broken down any further. 17, as I'm thinking through it, is also prime. So I'm already at my prime factorization for 51. It's just 3 times 17. All right, let's move on to the next one. And in the next one, we're going to be doing something a little harder. We need to find the greatest common factor for these two numbers. Well, what we're going to start by doing, we're going to start with a prime factorization. So I'm going to start by factoring 24. 24 is 2 times 12. 12 still isn't prime yet, so I need to break 12 down into its factors. 2 times 6. 6 isn't prime yet, and it is going to be 2 times 3. All right, so now I have my prime factorization of 24, but I'm not just dealing with the number 24. I'm dealing with 24 m cubed n to the fourth. So as you're finding the greatest common factor, what we're going to do is we're going to factor the first number and factor the second number. When we factor the first number, I'm just going to list all the factors in order. Notice that it's 2 times 2 times 2 times 3. Okay, I got that from my prime factorization, 24. Times m times m times m. That's from m cubed. Times n times n times n times n. That's from n to the fourth. So to factor out my variables, I'm just going to list them as many times as they're raised to a power. This is the same number as this right here. All right, let's take a look at the next part of this. I'm going to break down 32. I'm going to break down the other term, and I'm going to put it right below my top term. 32 is 2 times 16. Oh man, I know something about 16. I know that the prime factorization of 16 is 2 times 2 times 2 times 2. Let's see if that plays out that way. So it's 2 times 8. 8 is 2 times 2 times 2. 8 is 2 times 4 though, and then 4 is 2 times 2. It's all 2's. It's all 2's. So that means that 32 must be part of, like, if I think of raising 2 to a power, and I just keep going with it, 2 to some power has to equal 32. And in this case, if I count up the 2's, 1, 2, 3, 4, 5, it's 2 to the fifth equals 32. I'd verify that 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And that was 5 2's. So that makes sense. I'm going to list those factors out down below. Do I have 5 2's here? Yes. 1, 2, 3, 4, 5. Then I have m times n times n times n times n times n. I have 5 of those. That's good. Times p. Okay, now here's what I'm going to do next. To find the greatest common factor, I need to identify factors that are in both factorizations. So I'm just going to circle them. I actually have these circles pre-made here. So notice that 2 is in both, 2 is in both, 2 is in both, and then I run out of 2's because I ran out on the top term. But there are 3 2's in both of my factorizations. There's an m, and then there's 4 n's. So what do I do with that information? Well, what I can do is multiply the things that are circled back together. Those are the things that are in both factorizations. And when I multiply those back together, well, bam, greatest common factor. The greatest common factor of both of these terms is 8m times n to the fourth. And that's useful. What this means, what the greatest common factor between two terms is it's the monomial, which is a single term, okay, that can evenly divide into the terms of a polynomial. In this case, we have a binomial with 2 terms. So 8m n to the fourth will evenly divide into 24m cubed n to the fourth with no remainder. And it will also divide into 32m n to the fifth p with no remainder. So that is my greatest common factor.